Welcome back, students. In the last lecture, we learned how to calculate the change in entropy for a process. In this lecture, we will seek to apply entropy to determine the direction of natural change for a process. That is, to determine which processes will actually occur in nature. The learning goals for today are going to be to state the implications of the Clausius inequality, which will be involved in determining the spontaneity. We'll also be able to use the second law of thermodynamics and entropy to determine spontaneity. And we'll be introduced to the third law of thermodynamics, which allows us to measure absolute entropies for substances. Consider the example from last class. We talked about a metal bar spontaneously converting into two temperatures and decided that that probably wouldn't occur. Let's think about what would happen if we did have a metal bar at two different temperatures. So if we had two metal bars, one at temperature T1 and one at temperature T2, and brought them together, what would happen? We expect, using our intuition, that heat would flow from the hotter bar at T1 to the colder bar at T2. How can we describe this process thermodynamically? So what we're going to do is assume that heat flows reversibly and at constant pressure, meaning this bar is just out under constant atmospheric pressure. The heat of the process then from transferring from one to the other is a reversible heat, and it's also a constant pressure heat. Since it's a constant pressure heat, it's related to the constant pressure heat capacity times the change in temperature, which is also the enthalpy. So this heat is a state function. Of course, it's going to be related to the entropy of this process. The entropy for this process of heat transfer from one bar to the other is simply equal to the reversible heat for one bar over the temperature, and then plus the reversible heat for the second bar, and then divided by its temperature. What are these heats? Well, since we have an isolated system of two metal bars, the heat from one is simply equal to the negative heat from the other. So if heat is coming out of number one, it is going into number two. So they have the same magnitude and the opposite sign. And we're going to call this QP because it's also a constant pressure heat. So that means that the change in entropy is equal to QP over T1 minus QP over T2. And we can factor out the QP to get QP and then 1 minus T1 minus 1 over T2. So now we have a change in entropy. Let's imagine the two scenarios for this process. We could have, so we'll say that we have T1. So if T1 is hot and T2 is cold, this is a definition. We could change them if we wanted to. So let's say we have heat flowing from T1 to T2. If heat is flowing out of the hot bar T1, then that heat, QP, is negative. The heat is coming out of the system, so QP is negative. We can look at this term 1 minus T1 minus, or 1 over T1 minus 1 over T2. If T1 is hotter, this 1 over T1 is a smaller number than 1 over T2. T2 is colder. So for example, we could have 1 over 100 minus 1 over 90, and this number is also less than 0. So in the case that heat is flowing from hot to cold, our change in entropy is a negative number times a negative number, or a positive number. In the other situation, we could have heat flowing into the hot bar, so from the cold bar into the hot bar. What we would have then is heat entering the hot bar T1, so we would have a positive value there for the heat as energy goes into T1. This term here is still negative. So that would give, what that would give us is a delta S that is equal to a positive number times a negative number, or a negative number. So with this, we can pretty clearly see that the natural process has a positive change in entropy, and the unnatural process has a negative change in entropy. We can do another example, and then from then we're just going to assume that this is the case. This is something that's in general true for all processes. Natural processes have a positive change in entropy. Unnatural processes have a negative change in entropy. So let's go ahead and consider the compression of an ideal gas. This is going to be a spontaneous compression of an ideal gas. So this is, like we mentioned in the last lecture, all of the gas in the room going into one half of the room, so spontaneously compressing to half of its initial volume. We can calculate that using our terms here. So our change in entropy is always equal to the Q reversible over the temperature. And if we have an isothermal compression of these gases, the Q reversible is equal to the negative work reversible over the temperature. The work reversible, of course, for a compression of an ideal gas is simply negative nRT over V. So this will give us negative nRT over V over T. So we'll cancel out those, we'll cancel out the negatives. And then what we'll end up with is the integral of positive nR over V dV. Remember, what we're talking about is a compression from some volume V naught to half of its initial volume. So as we do this integral, we get nR natural log of V final over V initial. And plugging in numbers here, we get nR natural log of V final is V naught over 2, and V initial is V naught. So that is nR natural log of 1/2, which is also negative nR natural log of 2. And since the natural log of 2 is a positive number, and the number of moles in R, the gas constants, are also positive numbers, this is a negative number. This is less than 0. So with this, we can show that the spontaneous compression of a gas to half of its initial volume is unnatural. We do not expect that to occur because that would result in a negative change in entropy. Does this mean that we can never compress a gas? Of course not. We have all compressed gases in our lives. We've seen some examples of this and so forth. So we clearly can compress gases. What we need to compress a gas is some extra input of energy. So I would have to increase the external pressure of the gas, and then it would compress. So what this means, this is a natural compression, which means that it should have a positive change in entropy. To calculate this, we're going to have to consider both the entropy of the system, like we've done here, and also the entropy of the surroundings, and put those together to find a total change in entropy. And we'll do that at the end of the lecture. Before we get into that, however, we want to take some time to derive a very important thermodynamic relationship called the Clausius inequality. We're going to start by evaluating the total differential for internal energy, both for an irreversible process and a reversible process. du is simply equal to the differential of heat plus the differential of work. So we can have two different types of du. We could have du for an irreversible process, and du for an irreversible process would be dq. We don't really know what the heat for an irreversible process is, but the work for an irreversible process is simply the negative p external times dv. So this explains what du is for an irreversible process. For a reversible process, we have another thing we could do, where now for a reversible process, we have dq reversible, and the work reversible is minus p dv. We just spent the past lecture talking about what dq reversible is. We know that dq reversible is equal to ds, and then the dq reversible has to be over t. So that means we can say dq reversible is equal to t ds, and then subtract the work p dv. Why have we done this? Well, we've done this because internal energy is a state function. So we have an internal energy change for an irreversible process. We have an internal energy change for a reversible process. We know that the path doesn't actually matter for the internal energy. So these two things have to be equal because the internal energy change of a process is always the same no matter what path it's taken. It doesn't matter if it's an irreversible path or a reversible path. So we can set these two relationships equal to each other. So what we'll say is T ds minus P dV is equal to the heat for an irreversible process minus P external dV, because internal energy is a state function. Then what we're going to do is rearrange this. So we're going to bring this heat over to this side of the equation and bring this PdV over to this side of the equation. So when we do that, we'll get TdS minus the heat is equal to PdV minus P external dV. And we can simplify that by saying P minus P external dV. So we have this relationship here. From here, what we're going to do is actually look at this guy and see if there's anything we can say about it. So there are two possibilities that we could have with this. So we could have a situation where the pressure is greater than the external pressure. So the system pressure is greater than the external pressure. In this case, if this is true, P minus P external, the difference between them is greater than 0 because the pressure is larger than the external pressure. What about dV? So if the system pressure is larger than the external pressure, the system will naturally expand. That means the final volume will be greater than the initial volume, and the change in volume dV will be greater than 0 as well. What if we have the opposite scenario? So what if the system pressure is less than the external pressure? Well, in this case, P minus P external is a negative number because P external is larger than P. What about dV? Well, if P external is greater than the system pressure, the system will naturally compress, meaning the final volume will be less than the initial volume, and dV is negative. So if we look at this, no matter what our situation, P minus P external times dV gives us a positive number. Either it's a positive times a positive is positive, or a negative times a negative is positive. So P minus P external dV is always, always, always a positive number. It's always above 0. Now there's the small case where P is equal to P external, and that would be at a reversible situation. And then it would be equal to 0. So what we can say then is we have an inequality here. This is the Clausius inequality. So TdS minus the heat was equal to P minus P external times dV, but we just showed that P minus P external dV is always greater than or equal to 0. So that means TdS minus dQ is also always greater than or equal to 0. Now, the more common way in which this is written is the following. We usually say that ds is greater than or equal to dq over t. And this is a condition for any naturally occurring process. So here we have greater than or equal to. Sometimes we might only see greater than, and that reflects the fact that the equal to is only true of reversible processes for which there aren't really any examples of perfectly reversible processes. So in theory, a reversible process would have this be equal. For all other processes, it is greater than. So ds for a process is always greater than dq over t. And this is known as the Clausius inequality. Probably the only inequality you guys are familiar with previous to this in thermodynamics is the following, is dg, or I'll rather say delta g, is always less than or equal to 0. And we're actually going to derive this equation using the Clausius inequality, and we'll see that in a couple of lectures. So keep that in the back of your mind. Both of these are used for determining spontaneity of a process. With the Clausius inequality in mind, now we're going to be capable of solving systems that are not isolated. So how can we use entropy to determine the spontaneity of a non-isolated system? Our condition for spontaneity is simply that delta S be greater than 0. And for this, if we have a non-isolated system, our delta S is not simply the system entropy. So what we can say is that delta S total, the total change in entropy of the universe, is equal to delta S system, and then plus the delta S of the surroundings. Now, we often will not write delta S system. We'll just write delta S and assume that is the system delta S. That's what that means. So you may see that notation as well. And we'll say that this is greater than 0. So if the surroundings of the system has a negative entropy change, and the surroundings has a positive entropy change, and the surroundings is more positive and the system is negative, the total entropy change is positive, and that can actually occur. Now, how do we calculate the change in entropy for the surroundings? For this, we need to know the heat that enters the surroundings. The surroundings are much larger than the system, so any change in the system, such as change in the volume, change in the pressure, doesn't really change the volume or pressure of the surroundings. So if we have a system that's 1 liter and it compresses down to half a liter, if the surroundings are 100 liters that then increase to 100.5 liters, it's approximately a constant volume process. So therefore, the heat that enters and leaves the systems enters or leaves the surroundings at a constant pressure and volume. This is, of course, of the surroundings, not of the systems. So therefore, the constant pressure and constant volume heats are equal to either enthalpy or internal energy, and therefore a state function. So we can say something that's pretty radical, that the change in entropy for the surroundings is equal to the heat of the surroundings over T, and the heat of the surroundings is simply the negative heat of the system. So what we have here is the change in entropy for the surroundings being based off of the actual heat transferred between the system and the surroundings. The change in entropy of the system, however, is based on the heat transferred if the process was reversible. So what that means is that delta S for the system and delta S for the surroundings are not the same. So this is very different from other things that we've considered. So the first law tells us that delta U of the system is equal to delta U of the surroundings. Things like delta V of the system is also equal to negative delta V of the surroundings. But the entropy is not equal to the negative entropy of the surroundings because they use different heats to calculate them. Let's do an example of this. And we're going to go back to the example we had before, talking about compressions. So we're going to consider the entropy change for the compression of an ideal gas under constant external pressure from 25 to 10 liters. So from this, we have delta S is the system is equal to the reversible heat over the temperature, which is equal to NR natural log of V final over V initial, like we've seen before. If we have 1 mole of this ideal gas, we'll have 1 mole. We'll have R, which is 8.314 joules per mole Kelvin. And then we will have the natural log of the final volume, which is 10 liters, over the initial volume, which is 25 liters. Plugging in these numbers, we end up with negative 7.62 joules per Kelvin. So we might look at this and say, this is a negative entropy. This is an unnatural process. But before we do that, let's actually calculate the entropy change of the surroundings. So delta S for the surroundings is equal to negative Q of the system over T. In this case, it's equal to the positive work of the system over T. And since we have an irreversible compression, the work is equal to negative P external, which we'll say is the final pressure, times delta V over T. Using the ideal gas law, we can rewrite PF over T in terms of things we know, which is NR over V. So NR over V final times delta V here. And so we can go ahead and get this. We'll have negative 1 mole, 8.314 joules per mole Kelvin. The final volume is 10 liters, and the delta V is going from 10 to 25, so it's minus 15 liters. Plugging in all these numbers, we end up with 12.47 joules per Kelvin. So the total change in entropy is the sum of these two. So it's equal to negative 7.62 plus 12.47, which is equal to 4.85 joules per Kelvin, which is a positive number. So if we have an external pressure that is greater, so this example has checking the volumes, it's an isothermal process. We have an initial pressure of 1 bar, go to a final pressure of 2.5 bar. So if we put a gas at 1 bar under the constant external pressure of 2.5 bar, it will spontaneously compress, and we can see that as having a positive entropy. This line of reasoning can be used to show that for any naturally occurring process, the total change in entropy increases. I want to be clear here that what I mean when I say naturally occurring process is a process that occurs according to natural laws. In other words, the entropy of the universe is always increasing. Delta S total always has to be greater than 0. This line here that the entropy of the universe is always increasing is an alternative formulation of the second law of thermodynamics that is somewhat more intuitive to those of us who don't constantly think about heat engines. We have previously discussed how enthalpies of formation are obtained for all compounds, but what about entropies? We know that in the back of our textbooks, we not only have delta H naught formations, but we also have entropies for all these compounds. Laboratory experiments are typically done at constant pressure. So the reversible heat that is used to calculate entropy is also a constant pressure heat. So what we can do then is say that the delta S for a substance is equal to dq reversible over T like we always do, but that dq reversible is also a constant pressure heat. So not only is it equal to dq reversible over T, but it's also equal to the constant pressure heat capacity dt over T. So therefore, to get evaluation of the entropy, we need to consider the integral of the constant pressure heat capacity as a function of temperature. And so what we'll do is essentially integrate under functions that look like this. The heat capacity at constant pressure, as you can see by this graph, cannot be assumed to be independent of temperature, especially for solids. So for this regime, we can see it's pretty good for liquids and it's pretty constant for gases. We talked about how gases do add energy to the heat capacity as a function of temperature. So if you go up to very high temperatures, you would need to consider that as well. As long as there is no phase change, we can simply integrate under this function. So if we want to know what the entropy is at, say, 20 degrees, we can integrate under this function from 0 to 20 Kelvin and then figure out what that area under the curve is. But weird things happen at the phase change, and we'll see that on the next slide. Before I get to that, I want to mention the third law of thermodynamics. So the third law of thermodynamics is as follows. It says that the entropy of a pure, perfectly crystalline substance is 0 at 0 Kelvin. Now, what this makes sense according to our Boltzmann definition of entropy. Remember that Boltzmann's definition of entropy is the entropy is equal to K natural log of W, where W is the number of different ways you can arrange the system. If you have a system that's at 0 Kelvin and is not moving and is pure and perfectly crystalline, there is only a single way to arrange that system. So the entropy of that system is in fact 0. Now, why is this important for us? Well, what it means is that we know that the entropy at 0 Kelvin is 0. So that means if we wanted to calculate how the entropy changes, if we go from the integral from 0 to 20 Kelvin, if we know it's 0 at 0 Kelvin, we know that all the entropy we've added from 0 to 20, we actually now know the real absolute entropy at 20 Kelvin. This is not something that we can easily do with enthalpies and Gibbs free energies and so forth. So we always have those in terms of deltas. But with the entropies, we can actually calculate absolute entropy. So typically you won't see a delta S listed for a compound. You'll see an SM, and the M stands for molar. So you have the entropy of 1 molar substance at usually 298 Kelvin. We have a degree there as well. Now, if we want the entropy at a different temperature, we simply have to integrate. However, there are some problems, and those comes in at the phase change. So we can't integrate the function from here to here because we have a pretty big thing going on here as we're changing energy. If you think about a process, especially boiling, let's think about what happens to the entropy. So you have a liquid. Now, as that liquid goes from liquid to gas, what happens to the disorder of the system? Well, the gas takes up much more space than the liquid and moves about much faster. The disorder naturally increases, the entropy increases as well. How does it do that? We'll see that on the next slide. So we can calculate how an entropy changes at any temperature for any substance using this following equation. So starting at 0, what you can do is say, well, at 0, it's 0. So this number here would be a 0. And then we need to integrate the heat capacity of the solid as a function of temperature over the temperature at dt. And so we integrate that from 0 up until the melting point. And that will calculate the entire entropy that's contributed from the entire solid phase. During the phase transition, the enthalpy of that is the heat involved in going from solid to liquid. So the entropy change upon phase transition is therefore the delta H, the enthalpy of fusion, divided by the temperature at which fusion happens. And then we do the same thing for the liquid. We add the vaporization entropy change, and then we do the same thing for the gas. So looking here, we can see the heat capacity over temperature as a function of temperature. And we can see that if we integrate that, we get the following. Since the heat capacities are positive, the area under the curve is always positive, the entropy always increases as a function of temperature. And we see pretty big jumps at the phase change boundaries. I want to point out something that you may not be aware of. We'll talk about it later in chapter 8, but not all substances will have only 2 phase changes. So you can see here, there are multiple different solid states at different temperatures that have very different heat capacities. So to calculate the entropy for a substance like this, we would need more integrals here as we change from solid 3 to solid 2 to solid 1. In the next lecture, we're going to continue to look at entropy and go through some math with it, applying it as a state function. So not assuming the ideal gas law anymore, using our partial derivatives to work with entropy. And in doing so, we'll actually derive that expression for internal pressure that we saw way back in one of the first lectures.